You ever look at really complex systems like, say, an ecosystem or the stock market or even the way a city grows and wonder if there's some kind of deeper language connecting them all? A way to describe these incredible evolving patterns using the same set of rules? Well, today we're diving into a paper that tries to do exactly that. It's about finding a new universal blueprint for digital life. And at the absolute heart of all this is one profound question. What if the simple rules that generate all that complexity inside a computer simulation could be written not in code, but in the language that describes the very fabric of mathematics itself? It's a huge idea, and that's the quest we're on today. So, to get our heads around this, we've got to start with something called cellular automata. Now, you've probably heard of the most famous one, Conway's Game of Life. You know, where these super simple rules create patterns that seem to live and breathe and evolve all on their own. Okay, so the way these things work is honestly deceptively simple. You start with a grid, right? And each little cell has a state. Let's just say on or off. Then you define a really simple rule based on its neighbors. Something like, hey, a cell turns on if exactly 3 of its neighbors are on. And then you just apply that rule to the whole grid, all at once, over and over again. And what happens is just mind-blowing. You get these incredibly complex, totally unpredictable patterns. It's the perfect showcase of how simplicity can breed some serious complexity. So that's the idea, right? But how did mathematicians, the pros, actually write this stuff down formally? To really get why the work in this paper is such a big deal, we first have to look at the classical blueprint they've been using for decades. So traditionally, this has all been described using the language of sets. Think of it like a recipe. You have a set of ingredients. Those are your states, like black or white. You've got your container, that's the grid. And the rule is a function, a very precise instruction that takes one layout and tells you exactly what the next one will be. It's super concrete. It's all about the specific stuff inside the grid. But here's the problem. What if you want to talk about patterns and behaviors that are common across different kinds of systems? Focusing on the specific ingredients can actually be pretty limiting. And this, my friends, is where our story takes a really interesting turn. We're introduced to a totally new language for doing math, category theory. It's a way of looking at the world not by what things are, but by how they relate to each other. It's a game changer. So check out this shift in perspective. The old school classical view is like trying to understand a car by listing every single one of its parts, every screw, every bolt, every wire. It asks, what is this thing made of? But the categorical view, it's more like looking at a traffic system. It doesn't really care if a car is a Ford or a Toyota. It just cares about the object called car and the relationships, or morphisms, between it and other objects, like drives to a stoplight. It asks the bigger question, how does this thing behave and connect to everything else? It's a complete flip in how you see the world. Okay, so armed with this powerful new language, the researchers in this paper did something pretty remarkable. They used it to completely redefine the cellular automaton, creating a version that is truly universal. So this was the big challenge they put on the table. How do you possibly describe this dynamic, evolving system of rules and grids when you can't assume you're just dealing with a collection of elements anymore? How do you make it abstract enough to be universal? And here's their answer. Now, I know this probably looks like some scary, complex math, but for a second, just try to see it as a sentence written in this new language. All it's really saying is, a cellular automaton, that's tau, is just a special relationship, a morphism, that transforms one entire grid configuration, AG, into another one, BG, all happening inside some mathematical universe C. It's an incredibly powerful and elegant statement that changes the whole game. And the key takeaway here is generalization. C isn't just the world of sets anymore. It can be any mathematical world with its own rules. The alphabets A and B, they aren't just lists of states, they're abstract objects living in that world. And the rule tau isn't just a function, it's a morphism, a special map that respects the structure of whatever world it's in. They've basically just lifted the entire concept of a cellular automaton up into this higher realm of pure abstraction. So why go through all this trouble, right? It sounds kind of, well, abstract. But it's not just an exercise. By redefining the automaton this way, the authors unlock some really deep, fundamental truths about how these systems actually work. The power is all in the generality. See, when you prove something using this new framework, you're not just proving it for one specific type of automaton. You're proving it for an entire class of systems, all at once, no matter what they're actually made of. And the payoffs? They're huge. For instance, they come up with a new, much more powerful proof for a famous result in this field, the Curtis-Hedlund-Linden theorem. This theorem is a big deal. It basically lays out the fundamental properties that any cellular automaton rule has to have. And by proving it in their new framework, they show it applies to a way bigger universe of systems. They can even define automata that operate between totally different kinds of grids, like from a square grid to a hexagonal one. And they do it all with proofs that only care about abstract relationships, not the nitty-gritty details. So let's wrap this up and just think about what this all means. This work is really a testament to the incredible power of mathematical abstraction, of taking a step back to see the forest for the trees. This quote from the paper really says it all. They're basically saying, we refuse to be tied down to concrete things like sets. And because of that, they're forced to use methods that are more universal and, at the end of the day, just more insightful. They're focused on the pure underlying logic of the system. And that leaves us with a pretty fascinating thought to chew on. If the fundamental essence of a complex, evolving system, its rules, its behaviors, can be captured in a language that doesn't care what the system is physically made of, well, that suggests that complexity itself might be a universal property of relationships, like a kind of music that the universe plays, just using lots of different instruments. What do you think?